G'day, this here is the result of a whole lot of number crunching. We've got a sun tracker here. This actually uses an algorithm I downloaded from, is it the NOAA? They've got all this trigonometry in here to tell you where the sun will be anywhere in the world according to latitude, longitude, time zone and date. And I've had to throw a ton of tables in this, plus this extra algorithm on the end here to include the incline and azimuth of a panel, because that is on a horizontal surface. All of that trigonometry or astronomical data. And then you end up with a whole lot of tables we've got to process. So this here is the result of that processing, and we've got summer here, January in Australia. We've got winter here in June, July, and then out to December here at the end. So as you can see, even the figures form a bit of a graph. And then we've got metering, which is interval metering data, which pretty much comes in this format. The section in the middle here, the grey section are add-ons of algorithms to sort it out, pretty much in order of date. As you can see, I've extracted the year, the month, the day, the time, just so I can get it in organised day, time format. And then all of that data ended up in a big table over here up the top. Let's go up there, one for each month of the year, January, February, March, etc. They ended up being totaled. The best way to calculate yields is to match it with the half-hour interval. As you can see, my sun tracker does the same thing. Every half-hour interval is added up in a month. That's what we got here. So we got this yield page on the end here where it's all put together. There's the total there. That's just adding them all up from the three different arrays. They could be, well, in this case, we've got some test arrays there. Dead horizontal. Of course, those figures coincide with the dead horizontal figures of the NOAA software, which comes raw for a horizontal surface. And then we've got one pointing east and one pointing west. And with this data, you can see the west array is last to get the sun, and the last to not get the sun in conjunction with the horizontal surface. But of course, the horizontal surface is getting a lot less sun on it before it goes over the horizon than the one tilting to the west. So we get corresponding figures out here somewhere. Yes, that's, for example, here they're identical, east and west. One's pointing 90 degrees east, no, one's pointing 90 degrees west. And when I had all arrays horizontal after being processed through all of this algorithm here, mainly a filter. It's got basically that filters where the horizon is, all those add-ons. The horizon of a solar panel is going to be different to that of a horizontal surface, depending on its azimuth and pitch. So we've got these figures here. When they were all horizontal, they were all the same. Anyway, back to yield. And all those kilowatt hours got added up in their time, rather respective times, ready to pump into graphs. It's almost a graph as it is. And then we had a discrepancy. I always do a data check, to make sure the algorithms are all good with such vast amounts of data. And it wasn't. It was out by 2.331, and I'm like, where did I go wrong? But no, I threw in a bit of an algorithm here. Here it is. There's my algorithm to find it on the right-hand side here. Bit of stuff going on there. And it turns out at 2:30 a.m. they changed the meter from daylight savings time, or to normal time. So we got two readings for 2:30 a.m. So that's not my mistake. That's the Ausnet interval metering data's wrong. So there it is, caught red-handed. And there I was thinking I was wrong, but I was mistaken.